All right. Of course, in terms of analysis, it is actually not necessary to always use a primitive cell, right? In fact, if you can identify a unit cell that has convenient independent parameters, right? Independent directions that is perpendicular, then you should just use that because that'll be a lot easier to analyze. Okay, because if you can fit into the Cartesian coordinate system, then when you do analysis and to get the energy band structure, right, it's a lot easier to do than if you try and identify some axis that is sort of inclined to one another at different angles or funny angles, right? Okay, so a lot of times you choose unit cell that is convenient to use. Okay, so you need not always choose primitive cells. Okay, so in a three-dimensional sense, then this will be the kind of structure that we're looking at. So if you look at this figure 2.5, right, illustrating the lattice structure in 3 dimensions. So the red points are points in the front. You can think of it as points in the front. And the blue ones are the points in the middle layer. The green are the points in the back layer, the third layer. Okay. So in moving from one point in the lattice structure to another is basically just integer multiples of the three unique directions, integer multiples of each of these, and you add it up, you should be able to bring you to any points in the lattice structure. Okay, so that's essentially how you can get from one point to the other points. It's always integer multiple of this base unit in the three directions, and you add it up, then you get this vector that goes to the point that you want to go, right? So in terms of crystal, there is actually two important parameters that we need to understand that is commonly used to describe the crystal. Okay, one of it is the crystal direction, and the other is the crystal planes. Okay, so if you have a unit cell, okay, that has three independent vector direction, let's say A, B, and C. This A, B, and C values, okay, basically describes the dimension of the cell, right? And each of these values, A, B, and C, are known as lattice constants. Okay, lattice constants. So if you see lattice constant, automatically you should know that it refers to the dimension of the unit cell. Okay, the dimension in the three independent directions. All right. So of course, in a general case, if you look at a cubic unit cell,
you want to send them an email to ask them questions?
I mean, you can.
Someone has some questions.
Sorry, it's okay.
Okay, right. So for unit cell that is cubic in nature, that means the length of the three sides are all equal. All right, then you're A equal to B equal to C. Then the lattice constant is just a single value. Okay, if the three sides are all equal, then A equal to B equal to C. Okay, so coming back to the definition of a crystal, right? There's two important parameters that we commonly use. The first is the crystal direction. So if you look at the definition here, the crystal direction basically refers to the vector defining going from one point to another, right? So this is really the same as what you learn in your math under the topic of vectors, right? So this crystal direction basically refers to the vectorial direction from one point to another. Okay, so the definition of it is essentially the same. The only difference is in terms of how you write them. Okay, so in the case of describing crystal direction, we use this specific notation here, the bracket, okay, to define or to indicate that we are talking about crystal direction. Okay, so I'm not going to sort of read through these steps. Okay, this words here in the yellow box is the steps that you have to take to describe the crystal direction. Okay, but I'm going to basically illustrate this through an example. Okay, so that you can see how we actually do it, right? But bearing in mind that this crystal direction is essentially the same as vectorial direction. Okay, so in this case we have let's say XYZ, okay, of a the Cartesian coordinates. And let's say we have this unit cell here with the length of the site as A, B, and C. So in this case, this ABC, let's assume that in general they're not equal, right? Some ABC values describing the length of the three sites. So how do we describe, for example, the vector OA, right? From point O at the origin to point A on the edge of the cube. So the procedure is actually the same as describing vectorial direction. Okay, so we have your initial position, which is at origin, so it's 0A, 0B, 0C, and the final position is at a location of 1A, 1B, 1C, right? That's the coordinate of point A. So how do we describe a vector, right? If you want to write down the vector OA, then it's simply the final position of the vector, subtract away the initial position, okay, that you're going from. So in other words, it's the difference between the final position and the initial position. If you do that, okay, for the x direction, 1A minus 0A is just 1A, y direction, 1B minus 0B is just 1B, and z direction, 1C minus 0C is 1C, okay? And in the case of describing crystal direction, we actually don't indicate the lattice constants, okay? So what we do here is that we actually just need to drop the lattice constant, and that gives us 1, 1, 1. And in the case where the remaining numbers are actually not integer values, we need to take another step called the reduction, which is to change the quantities or to scale those quantities to integer value. So in this case, it's actually integer. So we're going to leave it as 1, 1, 1. Okay, so once you have that, all integers, then we basically just enclose it in a square bracket to specify the crystal direction. Okay, so in this case, we call this a 1, 1, 1 direction. The square bracket would basically tell you that this is referring to crystal direction. Okay, so this definition, or the procedure in determining this, it's essentially the same as finding vectorial direction. Okay, only difference is that we actually dropped the lattice constants, and we also scaled it to all integers when we describe crystal direction. Okay, let's look at another example, BC. So final position C has a coordinate of half A, right? In the x direction, the distance to that is half A, and then the y direction, in this case, it's in the xz plane, so y is equal to 0, so it's 0b, and the z direction, it's essentially 1c, right? It moves up by 1c to that position on the cube. And the initial position B is at a position of 1a, 0b, 0c. So to find the vectorial direction BC, right, we subtract final position for initial position. So if we do that, you get minus half A, 0B, and 1C. So remember, for crystal direction, we drop the lattice constant. If you do that, you get minus half, 0, and 1. So in this case, you notice that the x coordinate is minus half, or x direction is minus half, which is a fraction, it's not an integer. So we need to scale these numbers to integer. So in other words, we just multiply throughout by 2, and that gives us minus 1, 0, 2. Okay, and then we put it in the square bracket to indicate that it's referring to crystal direction. Now notice that in this case, there's actually also a negative number. So to represent negative number, right, for crystal direction, we actually don't put a negative number there. We put a bar on top of the number to indicate that it's like the complement. In other words, it's a negative value. Okay, so this is the notation that's being used to describe crystal direction.
Professor, what if it's a two-digit number?
Sorry?
Let's say, what if x is, let's say, a two-digit number? Like
X
minus 10. If let's say, for example.
Minus 10, then it's a bar above the 10.
Okay.
Yeah. So the bar is above whatever number there is associated to that particular direction.
Sir?
Yeah.
What if it is a fraction?
What if it's a?
Fraction, like half.
Sorry, say that again.
Fraction.
Fraction?
Yeah.
If it's a fraction, then you have to scale it to integer. So you find the common sort of lowest multiple and you multiply throughout by that, right? To change everything to integer.
Okay, thank you.
Yeah. Do you have an example? Like what specifically? What are you thinking about?
Like
what sort of
point C is half 0, 1. Then how to show that?
point what?
Point C.
Point C. Point C is point C is half A, right?
Yes.
So the coordinate of point C is half A, 0B, 1C.
Then how to show in the bracket form?
How to show in the bracket form? Oh, so you're talking about if it's OC, is it?
Yeah.
Okay, so if it's OC, then it will just be okay. So if it's just OC, right? Okay, so if you are looking at the crystal direction OC, then if you take these steps, it will basically be half A, 0B, and 1C, right? So if you follow the step, we drop the lattice constant, we're going to have half, 0, and 1, right? And you notice that one of the term is actually a fraction, so you multiply 12 by 2, right? To convert this to 1, 0, 2. So in this case, it is 1, 0, 2 crystal direction. Does it make sense?
Okay, thank you.
Yeah. Okay, so as long as you see a fraction in any of the terms, you need to multiply by a suitable integer to convert everything to integer values. Okay, that's the procedure that we use to define crystal direction. Okay, so the notation that we use to do that is this. So we just need to follow the steps.
Prof.
Yeah.
So what if there's like a 2-digit number? So like for like there's this vector with 11 units in the x direction, 1 unit in the y and z direction. How would I enclosure it?
11.
Yeah.
11 in the x. So it'll be 11a and what again?
1b and 1c.
1b and 1c. Okay.
How would you enclosure it?
Okay, so if it's 11A, 1B, 1C, let's say this is the final crystal direction, right?
Yes.
Then we drop the lattice constant, you get 11, 1, 1. Then it's all integer, so we just put it into the square bracket. So 11, 1, and 1. So this is like writing this vectorial representation with like a square bracket. So you need to separate the numbers. You don't clump them together.
I see. Okay.
Yeah.
Thank you.
So you must put a gap between the three quantities.
Okay.
Right. So there must be a gap between them. I mean, here I did not sort of put the gap because I don't know, maybe it didn't show out so good. There should be a gap between the numbers so that it's clear that it's 3 different numbers.
Oh, okay.
Yeah.
Professor.
Thank you.
Yeah.
When we are asked to, let's say, determine factor OA, which has been given on the slide,
Okay.
do we have to write like, final position is what, initial position is what, factor A, OA is what?
No. Actually, if it's straightforward and it's clear what it is, you just write it down straight away. I mean, basically we have this here to basically illustrate the steps, right? That it is final position minus initial position that gives you the vector, and then followed by dropping the lattice constant, do a reduction, and then you put it in the square bracket.
Okay, thank you.
Yeah, so if it's clear, actually you don't even need to show this table,
Okay, thank you.
Yeah.
Professor, what happens if it's like square root A, 1B, and 1C?
Square root A,
Yeah, or is it we don't involve square roots?
Well, I mean, if you think of in the context of what we're trying to define, right, it's actually crystal direction, and crystal direction will mean going from one point in the lattice to another point. Under what circumstances will you get square root A?
Oh, okay, can.
Yeah, you won't get that situation. It's always integer multiples of the 3 directions.
Okay,
right?
thank you.
Yeah.
Prof.
Yeah.
So what happens if my vector OA is like 10, 10, 10? Do I scale it down to 1, 1, 1?
Yes. Yeah.
Okay.
Yes. Yeah, actually, if it's 10, 10, 10, in terms of writing the crystal direction, you can leave it as 10, 10, 10, but the 10, 10, 10 is essentially the same as 1, 1, 1. So usually we just reduce it to the smallest.
Okay, thank you.
Yeah, so there's no difference between, say 10, 10, 10 and 1, 1, 1. It's essentially the same crystal direction. And most times, the reason why I scale it down is also because when we analyze the crystal to derive the energy structure, remember we say we use just the unit cell, right? Usually we just reduce and look at the smallest one, or the one of the smallest representative ones. So we don't really need to consider like a big structure like a 10, 10, 10,
Okay, Professor, just a last question.
Yep.
For enclosure, it's just the simplest ratio of the vectors, is it? Basically, of the vector numbers, just the simplest ratio of the vectors numbers.
Simplest ratio of the
Vector numbers.
vector numbers. Don't quite understand what you're saying.
Basically, like the ratio.
Uh-huh.
The ratio of all the vector numbers is the enclosure is just the ratio of the vector numbers x, y, z.
Yes,
Like-
yes.
Okay,
yes.
okay.
That's right.
Because like when just now the person give the illustration of the 10, 10, 10,
Yeah.
then you said simplify it to 1, 1, 1. So it's
Yeah,
just the ratio, is it? Okay.
Yeah,
Thank
you basically reduce to the smallest possible, right? If there's some common factor in each of the terms, you can actually just take out the common factor. So it's not essential to have that there. So you can just reduce it to the smallest.
Prof.
Yeah.
Could I ask, is it necessary to simplify it? Like, if, in case of me forgetting to simplify it, would there be penalization?
Well, I guess we will probably still mark you correct because essentially it's still, it's the right answer. It's still the right answer. I mean, the crystal direction is still the same, except that you did not reduce it. So I guess typically we'll just let you off and mark it correct.
I see. Thank you.
Okay.
Hello, Professor. Can I just check with you, what will be the lattice constant for this vector BC?
Sorry?
What will be the lattice constant for the vector BC represented on the screen?
Lattice constant for the BC.
Yeah.
So the lattice constant would take on the values of the lattice itself. So in this case, if the lattice constant in the three directions are ABC, then in terms of actual vector, right, it will be you talk about BC. So the actual vector would be minus 1A, 0B, and 2C. The actual vector size. But in terms of, if you look at it, if you think about it, this crystal direction that we're defining is actually kind of like a normalized quantity. That means because this ABC is fixed, right? So essentially, we're just taking it out and just describe it in terms of the sort of representative units of it.
I'm sorry, but I thought the lattice constant was supposed to be like the unit of measurement for the size of the
three independent directions.
Oh. So in this particular case, could A, B, and C be different values?
Yeah, it can be.
So
we
that
describe.
So that would mean that in this situation there are three different lattice constants?
Yes. In this case.
Okay, thank you.
But in actual case, if you look at the crystals that we consider, right, for semiconductor, a lot of times the A, B, and C are the same. In other words, most times we're dealing with cubic unit cell. Okay, so this in this particular example, I just bring ABC as a generalization, so that it's so we make it general. But in actual case, when we analyze semiconductor, most times they are cubic unit cells. So the A, B, and C's are all equal in values. Okay. So any other questions? If not, I'll continue. Right, good. Okay, now the other parameter that we would describe in crystal is what you call the crystal planes. Okay, so the crystal plane is basically specified by this quantity called the Miller indices. It's also in a format that's quite similar to crystal direction. Only difference is that in terms of the bracket, right, we use a round bracket instead of a square bracket. Okay, so of course, before we talk about the step to describe a plane, okay, let's step back and think about in the case of vectors, right? You know, I suppose you guys have done vectors already or not yet? Has everybody covered vectors already in your H2 math?
Nope.
Yep.
No? Yes?
Covered.
Some?
Yes.
Okay.
Yes.
Okay, perhaps O level, you guys may have learned it. Do you all learn vectors in O level?
Yep. My basic
Yeah,
2D
some
Yes.
math.
2D. Yeah, okay. Okay, so anyway, we know that in this vectors, right? How do you describe a line? Okay, we basically describe a line by having some knowledge of a point on the line and then the direction of the line. Okay, so in other words, if you look at it in general, the equation of the line in the vectorial form is R equals to A plus lambda B, right? Where A is a point on the line and B is the direction of the line or the gradient of the line. In the case of a plane, for those who haven't learned, we can actually describe the plane using kind of a similar format to this discussion on line, right? Okay, maybe I write down the equation now. Okay, so for a line, we know that a point on the line, R, the position vector of a point on the line is equals to R equals to A, okay, which where A is a point on the line, some known point on the line, plus lambda. Lambda is some variable, B, right? B is the vector that is parallel to the line. In other words, this B here describes the direction of the line, right? The inclination of the line. Okay, so this is for line, right? Now, what about planes? So planes will be, in general, 3-dimension, okay? So to describe the position vector of a point on the plane, we basically can just extend the description for the line. So it's A plus lambda B, right? A is a point on the plane. B is a direction that is parallel to the plane. And then plus, in fact, another quantity that's a mu, C, where C is another direction that is parallel to the plane, where B and C are not parallel. Okay, so if you know two vector direction that is parallel to a plane, and you know a point on the plane, you can actually write down a vectorial equation, right, for a point on the plane. So that's one possible definition, okay? In fact, another way to write this, for those who have learned it now, will be R dot N equals to A dot N, right? Where N here refers to a vector that is perpendicular to the plane. Okay, and A is still a point on the plane. Okay, so in other words, if you want to define a plane, based on this description, right, the quantity that you need to know is a point in the plane, let's say point A, with a position vector of A, right? So it's OA now, in other words. And if you know also another quantity, which is N here refers to a normal to the plane. If you know what is the vector that's perpendicular to the plane, you can then use it to describe the plane. Okay, you can write down an equation for the plane in a vectorial form. Does this look familiar to some of you?
Yes.
Okay, right, great. Okay, so bottom line, for those who haven't learned this, don't worry. Just appreciate, right? If you want to describe a plane, the important quantity here, right, especially the direction of plane, it is actually the normal to the plane. If you know the normal to the plane, then you know what plane you're looking at. Okay, so in the case of crystal direction, in fact, this Miller indices, okay, this Miller indices is basically a vector that is perpendicular to the plane. In other words, this Miller indices is the n. It's the n here. Okay, it's the n here. Okay, so that's what basically Miller indices is about. Okay? Okay, so that's the background to Miller indices. So in a crystal form, right, when you define a plane, in fact, we are not particularly important, well, not particularly bothered about the actual position of the plane. Because if you look at a crystal, if you identify a plane, right, you can actually find another plane that is displaced at periodic distance. Okay, because remember, crystal, the atoms are actually periodically arranged. So if you have a plane, you'll find another plane at some fixed distance away. Okay, so it's actually periodic. So we don't really distinguish one plane from another that's parallel to one another, right? So we are only focusing on identifying what is the orientation of the plane in the crystal. Okay, so that's why we're only concerned with finding out the essentially this Miller indices, which is the vector that's perpendicular to the plane. So then, of course, the question is how do we actually determine this Miller indices? Then how do we determine the normal to the plane in the crystal? So again, in this yellow box, that's actually the steps that is listed out for you. Okay, telling you how to do it. So again, I'm not going to read through this. Okay, I'm going to run through it by looking at some examples. Okay, I think for that example, you will know what is the step that's involved. Okay, so let's look at A. So let's say we want to describe this plane here that is shaded in blue. Okay, in a unit cell like this. So how do we find out what is this Miller indices of the plane? So first, what we do is that we determine the intercepts of the plane with the three independent axes. Okay, so in this case, we are using the Cartesian coordinate. So it's quite straightforward, right? So if you look at the x-axis intercept, it's cutting at position A from the origin. Okay, so that's 1A. And the y-intercept, okay, this plane basically cuts the y-intercept at point B. So that's 1B for the y-intercept. And for the z-axis, notice that this plane is actually parallel to the z-axis, which means that it doesn't intersect. So the way to write this is that you can think of it as being extended to infinity and still not cutting. So you need to go to infinity, right, to have any chance of intersecting, which actually is not quite true also. But we kind of put it as infinity of C to specify that it's parallel to the z-axis. Okay. So once you determine the intercepts, then what we do here is that we drop the lattice constants, right? Similar to crystal direction. So that gives us 1, 1, infinity. And then we take the reciprocal of these numbers, and that actually gives us 1, 1, 0, right? 1 over infinity, 1 over a very large number will give you approximately 0, okay? So the remaining numbers we get is 1, 1, 0. And then we do a reduction again. So in this case, it's all integer. There's no fraction here. So we just leave it as 1, 1, 0. And then we put it in a round bracket to complete the description of the Miller indices. So in this case, we call this the 1, 1, 0 plane. Okay, so the bracket used tell you whether you're looking at a plane or whether you're looking at a crystal direction. Okay, so you have to remember that if you see a round bracket, this actually describes a plane. If you see a square bracket, then it's actually describing a crystal direction. Clear? Okay, let's look at another example. Okay, this triangular plane here that's sort of cutting the cube at some inclined direction. So again, if you write down the intercepts at the three axes, you have 1A, 1B, 1C. Drop the lattice constants. So that gives us 1, 1, 1. Take the reciprocal. Okay, still 1, 1, 1. So these are integer, we don't have to do any reduction. And this is called the 1, 1, 1 plane. Okay, this is a 1, 1, 1 plane. Right? So if you understand the approach, then it's fairly easy to find out the Miller indices of a crystal plane.
So can I ask, actually, what is the function of Miller indices?
The Miller indices is to describe the plane, and this is kind of important because in semiconductor, right, when we analyze the crystal, there's a need to describe which plane you are considering.
Oh, okay.
Yeah, so that's why we need to understand how this is defined.
Okay, can.
Yeah, so it's used, when we are talking about semiconductor crystal or analyzing semiconductor crystal. That's why there's a need for me to tell you how they are being described.
All right. Okay.
Yeah,
Thank you.
Yeah. Okay. Can Okay, so now in terms of crystal structure, if you look at all the crystals that we find on Earth, right, you will find that all these different type of crystal that we find on Earth can actually be described by 14 basic crystal structures. In other words, all these crystals that you find, right, you find that if you break it down into small unit cells, okay, you can this unit cells that you can find is actually similar to a lot of other ones. Okay, so if you identify all the unique basic crystal structure, there's a total of 14 different crystal structure that you can find. So in other words, all the crystals that you find, they'll fit into one of this basic crystal structure. Okay, and out of this 14 basic crystal structure, 3 of them are actually cubic in nature. Okay, and these 3 cubic structures are shown here. Okay, the simplest one is called the simple cubic structure, where the unit cell is in the shape of a cube, obviously, because it's cubic, right? So the lattice constant on the 3 sides are all equal. Okay, and the other important point here is that the lattice points are at the corners of the cube. Okay, so you get lattice points at just the corners of the cube. So in the case of a simple cubic structure, if you look at the unit cell like this, then you see that there is a total of 8 lattice points. Okay. Now the other 2, right? The next one is what we call the body-centered cubic structure, which has lattice points not just at the corners, right? Other than the corners, you also have one in the middle of the cube. Okay, so this one in the middle here is additional, and which means that in the case of this particular cubic structure, this is called a body-centered cubic structure. There's a total of 9 lattice points. Okay, and then the last one is called the face-centered cubic structure, where in addition to one at the edge of the cube, you also have one on the center of each face. Okay, so we know there is a total of 8 at the corners, right? And in the case of a cube, there's a total of 6 faces, right? 6 faces. So, which means that you have 6 lattice points on the center of each face in total. So 8 plus 6 will give you 14 lattice points. Okay, so there is actually these 3 cubic structures that you can find, the basic cubic structures. And in fact, another important quantity that we usually will calculate for crystals, right, is what we call surface densities, which define how many atoms you can find per unit area of a plane in the crystal. Okay, so that surface density quantity, right, is used to describe how many atoms you find per unit area in a plane of the crystal. There's another quantity that we also calculate. Okay, that's called the volume density of atoms in the crystal. Okay, so as the name implies, this is used to determine how many atoms you have per unit volume in the crystal. Okay, so in this course, you need to know how to calculate this too. Okay, so we're going to sort of illustrate how to do this. In fact, the tutorial questions, there is some questions regarding this, calculating the surface density and volume density in a crystal. Okay, so the crystal structure in the case of semiconductors, right? The common one, materials like silicon and germanium. Okay, these are actually 2 of the most common semiconductor that you can find. In fact, in the early days, as you recall, right, from the introduction on Tuesday, if you have noticed, right, the first semiconductor material that was actually used to demonstrate diodes and even the transistor is actually based on germanium. Okay, because germanium was something that scientists and researchers started with lah. But of course, subsequently they don't just use germanium for realizing this electronics and IC chips, primarily because germanium is not so commonly found. Okay, the material is quite rare, so which means that the cost is quite high. The cost of germanium is much higher compared to materials like silicon. Okay, silicon it's actually in abundance. Silicon is basically sand, right? You can find it in sand, so it's we can find it easily everywhere. So the cost of this actually will be a lot cheaper, and that's why subsequently we have silicon as the main workhorse, right, for semiconductor electronics and all this. Is largely based on silicon material. Okay, it's at the end of the day it boils down to cost, right? I mean, if you use germanium, then you will expect all these electronics that we have now will be multiple times more expensive than if we were to just use silicon. Okay, so it's all driven by cost, consideration. Anyway, if you look at elemental semiconductors like silicon and germanium, okay, and you look at the unit cell of such crystals, okay, their unit cell will look something like that with atoms, okay, in the unit cell. So you have essentially, if you follow, right, you have atoms at the corners of the cube of the unit cell. By the way, silicon and germanium are basically have the cubic structure. Okay, so you find that the unit cells is in the shape of a cube. Okay, so you have atoms at the corners of the cube, and at the same time, notice that they also have atoms at the center of each face. Okay, so I try to color this for you. Okay, so center of each face will be this guy, this guy, this guy, this guy, and this guy at the back. Okay, so these guys are and the one at the bottom. Okay, so these atoms are basically sitting on the center of each face. Okay, so other than those at the corner, you have one each at the center of each face. In addition, you also notice that there is also another 4 within the cube itself, which is this in green. Okay, these 4 are actually sitting in the volume of the cube. Okay, so all in all, right, for the case of unit cell or silicon and germanium, right, how many atoms do you have? You have 8 at the corners. You have 1 on each face, that's 6. So let me write that down. So it's 8 at the corners, 6 on the center of each face, and another 4 in the volume itself. Okay, so in total we have how many atoms? 18. Okay, so in this unit cell we have 18 atoms, and so this kind of structure of silicon and germanium are called the diamond crystal structure. Okay, this is actually called the diamond crystal structure, and in fact, in this unit cell, the smallest one that you can use, right, to define the crystal structure, it's actually this one that is highlighted in the dashed line or blue now, right? So if I were to highlight it, okay, this in this volume here is actually the primitive cell. Okay, this is actually the primitive cell, which is made up of 1 here, right, and another 4 at the corresponding position. And in fact, this 4 surrounding this one in the middle form what we call a tetrahedral structure, right? It's essentially like 4 triangle. It's a structure with 4 triangle sides. Okay, 4 triangle sides. This is a tetrahedral structure, and this is, in fact, something that's not surprising, right? Because the distance of each of these 4 from this center one here, it's at equal distance. And in fact, it's this 4 that is sharing electron with this atom in the middle, right? Remember, for silicon, they need to share electrons to form covalent bonding. Okay, so this is their structure that is sharing. Okay, so in 3 dimensions, it's actually space in different directions. right? Of course, in terms of illustration in 2D, you know, the diagram that we showed earlier, we just show them placed side by side. Okay, that's just for illustration. But the actual distribution or the arrangement is actually this. Okay, the 3D arrangement is actually this. This is the primitive cell. When we analyze silicon crystal or germanium crystal, we usually will not use a primitive cell because, you know, the direction is awkward, right? The position of the atoms to each other is awkward. So if you want to use this to analyze, it's harder, right? It's not impossible, but it's harder. So typically we just use this big unit cell, the cubic unit cell, to describe the crystal structure. Okay. Now, and this diamond crystal structure, right, is fundamentally the face-centered cubic structure. Okay, you can actually derive this from the face-centered cubic structure, lattice structure. And why is that? Because if you start with the if you start with the face-centered cubic structure, what do you say about the face-centered cubic structure? It actually has lattice points at the 8 corners of the cube, right? Okay, so these are the points where you would find essentially atoms there. And for face-centered cubic structure, what else do you have? You have one each on the center of each face, correct? Okay, then that in fact leaves us this 4 that is in the body. Where does this lattice point come from? Okay, it turns out that to construct the diamond structure for the face-centered cubic structure, we actually do not just put one atom at each of the lattice points. In fact, the atoms that we put at the face-centered cubic structure lattice points, it's actually not a single atom. It's actually a set of atoms. Okay, and this set of atoms, it's actually this set here, right? Okay, so if you imagine you start with the face-centered cubic structure, right, and you put this set of 2 atoms at each of the lattice points. Okay, if you do that, then you can actually construct this diamond crystal structure. Let me show you how this is so. Okay, so I place this at each of the lattice points of face-centered cubic structure. So at this corner here, if I put that pair there, right, I'm going to get this. I put a pair at this lattice point, I'm going to get this. At this lattice point, and the other corner is there, right, and this guy is there. This guy will be there. At each of corner, that's what you get, and of course at the other corner you get this, right? And then at the center of each face, I also put this pair there. Okay, so this guy will be outside. The one at the back will be outside, and end up, the one that is at the front face, right? If you put a pair of atoms there, then you actually get this guy that is in the body. If you put this pair of atoms at the lattice point on the left center or left face, then you get this pair. And at the bottom face, you get this pair, right? And what else? 1, 2, 3. Okay, then at this guy here, when you put it, you get this. Okay, so if you put it there, then you get this. So if you don't consider those atoms who are actually sitting outside the cube, okay, then and you basically take those away, right? This is outside a cube, this is outside a cube. The extra one is outside, so we don't consider those because this will contribute to neighboring unit cells. And what you have left is this 4 atoms that is within the unit cell. Okay, so in other words, a diamond crystal structure is fundamentally the face-centered cubic structure with a pair of atoms, right? The basis of atoms is actually these 2 atoms with a direction that is along the main diagonal of your cube. Okay, so if you put it into the face-centered cubic lattice structure, you can actually get the diamond crystal structure. Okay, so the bottom line here is that the underlying lattice structure, right, of the diamond crystal structure is the face-centered cubic structure. All right. So one important property here, which I just mentioned, right, is that the direction of this Okay, the direction of this basis atoms, right? This pair here, if you extend it, you will touch the atom at the other corner. So in other words, the direction of this pair of atoms is actually along the main diagonal of your cube. Okay, the orientation of it is along the main diagonal. So each of these ones that you see, right? Okay, this guy here, this direction and this direction is parallel. Okay, they are actually parallel. Okay, the direction is the same. Okay, and the other important property is that this the other property is that the length of this pair of atoms that you put at each of the lattice points, the length of this is actually a quarter of the main diagonal length. Okay, let's say the main diagonal length is m, right? Then the spacing between these two atoms in the basis is actually a quarter of m. Okay, that's the property of the diamond crystal structure. Okay, the silicon atoms or the germanium atoms are actually spaced apart with a quarter the length of the main diagonal. Okay, this pair here. So in other words, this other pair. Okay, this other pair, the length of this is also a quarter m. The length of this guy here is also a quarter m. All right. Okay, that's the basic properties of this unit cell of a silicon or germanium. Okay, commonly known as the diamond crystal structure. Now, there's also another identical arrangement, but if you use different atoms, okay, like in the case of this particular one that you see here, where the basis atoms, right, instead of using two identical elements, I use two different elements, okay, like gallium and arsenic, right? So notice that the pair of elements is different. Okay, in this basis atoms that you put at each lattice point of the face-centered cubic structure, if you use different elements like gallium and arsenic, then you get this structure here called the zinc blende structure. Okay, this zinc blende structure is basically the crystal structure of binary compound semiconductor like gallium arsenide, okay, where you have gallium and arsenic atoms, or indium phosphide using indium and phosphorus atoms. Okay, the arrangements of the atoms looks very similar to that of silicon and germanium, right? Except that the atoms are alternating elements. Okay, then this gives us a different semiconductor crystal. Okay, so the one that has different atoms, right, in each of the positions, alternating atoms in the atom position of silicon, then we call this a zinc blende structure. Okay, and gallium arsenide indium phosphide has this zinc blende structure. Okay, and arrangement wise is all the same. Of course, the difference here will be in terms of the lattice constant. Gallium arsenide, for example, right, when they form into a crystal, the unit cell, the lattice constant will be different from the lattice constant of a silicon unit cell. Okay, but other than that, the arrangement is the same, right? Arrangement in terms of how the atoms are positioned and orientation. So what I'm saying also is that this separation between the atoms, right, this length here is also still a quarter of the length of the main diagonal. Okay, of course, the length of main diagonal is different in gallium arsenide and silicon unit cell. Okay, but this length between these basis atoms is still a quarter of the main diagonal length. All right, so these are basic property that you should keep in mind because in the subsequent tutorial questions, some of it requires you to do some calculation on these unit cells. All right, so
Professor,
yep.
why is the lattice constant different since they have the same structure, crystal structure?
The lattice constant is
similar.
different because the atoms are different, right? I mean, the different elements that's used to construct the crystal, the atomic weight and all that is different. You know, so and the outermost electrons are also at different shells. So when you put them together, their spacing will also be different, and that results in the different size unit cells.
Thank you.
Yeah. Okay, so Right. Okay, so coming back to this calculation of these two quantity for crystal structures, right? We mentioned that in crystal structure, we need to know how to calculate things like surface density, volume density. So here we're going to just go through an example to show you how to calculate surface density of atoms on a plane in a crystal. Okay, so in this example, we have, let's say, a silicon crystal, and the lattice constant is given. So this lattice constant refers to the dimension of the cube. In other words, this A quantity here. And so you see that the unit that's given is 5.43 angstrom. Angstrom is another unit of measure of length. Okay, and if you look at this description here, 1 angstrom is 10 to the power minus 10 of a meter. Okay, so this is actually a measurement of very, very small dimension. Okay, so just bear in mind that 1 angstrom is actually 10 power minus 10 of a meter. So 5.43 angstrom is actually very, very small. If you convert to nanometer, right? It's actually 0.543 nanometer, right? 0.543 nanometer is very, very small. Okay, if you look at, let's say the thickness of your hair, right? Thickness of your hair is in the range of 100 to 150 micrometer. Okay, so in the thickness of your hair, that is tens of thousands of atoms. If it's actually a crystal. Okay, that's the kind of dimension they are looking at. So the unit cell is actually very, very small. Okay, so coming back to the question, let's say we have this plane here, and we want to find out what is the surface density of atoms on this shaded plane, right? In this case, the shaded plane is 0, 1, 0. So what we do here is that first we take out this plane, okay, and we can see that on this plane, the atoms that are sitting in the plane will be the 4 at the corners, and you also have 1 on the center of the face of the plane, okay? So, so the question we're trying to answer is how many atoms are there per unit area of the plane? Okay, so this plane is this plane here, right? So you need to find out what proportion of the atom is in the plane. So obviously, if you look at those at the corners, right? Those are the corners. And if you put similar squares on the edge, then obviously you can see that in the shaded plane, only a quarter of the atom is within the plane. Okay, the other quarters are actually in other planes outside this plane. So the same goes for the other 3. So we can see that the atoms at the corners basically just contribute a quarter of its atom to the plane that we're considering. Okay, so there's a total of 4. So total number of atoms that is within this plane out of this 4 will be a quarter multiplied by 4. And obviously the one that's sitting in the middle, this whole thing is in the plane, so we count that as 1. And in this case, we get a total of 2 atoms. Okay. So to find surface density, other than number of atoms, we also need to find out the area of the plane. So this is just a square. So the area of square is just a square, right? Because you know the length of the side of the square is a, and you take number of atoms divided by the area, and that gives us 2 over a square. And a is a lattice constant, which its value is given. So if you convert it to centimeter, it will be 5.43 by 10 to the power minus 8 of a centimeter, right? And if you work that out, you get about 6.78 by 10 to the power 14 atoms per centimeter square. Okay, so in this particular plane, you get 10 to the power 14 atoms in cubic centimeter of the plane. Okay, so that's lots of atoms in that plane. All right. So that's how we calculate surface density, okay, in a plane of a crystal. Now, what about volume density? So volume density would be quite similar, except that in the case of volume density, we look at what volume of the atoms is within the unit cell that we're considering. Okay, so in this case, we're just looking at the 2 dimension, right? How much of the 2 dimension of the atom is in the plane? Okay, in the case of volume density, we consider how much volume of the atom is within the volume that we're considering. Okay, so this would help you to calculate the volume density. Anyway, there's some questions on this in the tutorial, so have a go at that. During the tutorial, we would discuss this, all right? Okay, so okay, perhaps we can go for a 10 minutes break. Okay, let's go for a 10 minutes break. The time now is 5:20. Okay, let's come back at 5:30 to finish up the other half of today's lecture. Okay, let's go for a 10 minutes break.
Sorry, Prof, can I ask a question really quickly?
Sure.
How did you derive 5.43 times 10 to the power minus 8?
Okay. The lattice constant, if you refer to the question, right? Lattice constant is 5.43 angstrom, correct? So 5.43 angstrom would correspond to 5.43 by 10 to the power minus 10 of a meter, right? If you convert it to centimeter, we multiply this whole thing by 100, right? Because 1 meter is 100 centimeter. So you multiply by 100 centimeter, then this quantity here becomes minus 8.
Okay, yeah, thanks.
Yeah, so that's how we get the 5.43 by 10 to the power minus 8 of a centimeter. So it's just converting the unit.
Hello, Prof.
Yep.
So is atoms per cm square the SI units or for surface density?
Sorry, say that again.
Is atoms per cm square the SI unit for surface density?
It's the standard notation. Let's put it this way. It's not exactly a SI unit. I mean, it's the standard notation that we use to describe the surface density.
Okay, so if they don't mention what units to use, we default to this, right?
Yes. If the question did not specify, you put it as, for example, atoms per meter square. That's fine as well. But in the area of semiconductor, right, you find that the standard notation is for surface density, we put it in per centimeter square.
Oh, okay. I have one more question.
Yeah, sure.
Just now in the crystal planes part,
yes,
it said planes cannot pass through the origin. Why is that so?
Okay. The problem is that if you have a crystal plane that passes through the origin and you have to follow through this procedure, then your intercept will be 0, 0, 0, right? And if you take the reciprocal of 0, 0, 0, then you just get infinity, infinity, infinity. Then you don't get any representative number to write down. Okay, and so in the case where you meet a situation where the plane is at the origin, then what you can do is to shift the coordinate system out from the plane. That means shift the plane out from the origin to another location so that it's still parallel to the initial plane that's passing through the origin, and then use that to derive the Miller indices.
Oh, so like scale the thing by
translate.
Translate.
Yeah, you move it. Yeah, that's right. Because anyway, the whether this plane or this plane, as long as they're parallel, right? One of it passed through origin doesn't matter. Is in terms of description or Miller indices, they are the same. So you can just translate it to a convenient location and determine the Miller indices.
Okay, thank you.
Because we don't distinguish between different planes. This plane and this plane is the same. It's periodic, so we don't distinguish between one another.
Okay, thanks.
Okay. Okay, we can go for a break. Come back at 5:30.
Hello, Professor.
Yeah, sure.
May I ask, the surface density in exercise 2.3, does it apply to any plane along that direction?
Does it apply to, sorry, what again?
Does this number apply to any plane along that direction?
Does it apply to any plane along
as long as it's 0, 1, 0.
Sorry, I can't hear you clearly. Can you repeat?
Sorry. I mean that this surface density apply to any plane as long as it's 0, 1, 0.
Yeah. As long as it's the same plane, then it will be the same for the same crystal, of course. If you move to another crystal, the spacing is different, then the density will be different.
Okay, thank you.
Yeah.
Prof, I have a question.
Yeah, sure.
So usually for like a corner atom, the nearest atom to this corner atom would be inside the unit cell, right?
Sorry, can you repeat again?
Okay. So like the closest, like the distance between two atoms for
Yes.
the crystal structure is A000 and A4, right?
Yes.
So
The
usually,
tetrahedral structure is the closest
yeah.
atoms.
Yeah. So usually the closest atoms for if one atom is out in the corner atom, would the other atom be inside the structure? Like the cubic at the unit cell.
Yeah.
Oh, okay.
Sorry, your question is, would it be
like would the nearest cell the atom bonded to this corner atom, would it be inside the unit cell or within the plane of the unit cell?
Which, okay, let me see. Let me pull out the figure. Okay. You talking about this?
Yeah, this one.
Okay. Which specific ones are looking at?
So, like for example, the atom at 000.
Okay.
Would the other atom that is attached to this atom be inside this unit cell, or would it also be at the plane?
The atom that's attached to this,
Yeah.
So the nearest one will be this guy, and it will have another one here, right, on this side. And then it will have, okay, let me see. You will have one on this side and one on this side, which is outside the unit cell.
I see.
Yeah.
So it won't be at like the center of the face or on another corner cell, right? On another corner.
No. So basically, when we draw a unit cell like this for a crystal, we need to draw those that is on the unit cell or in the unit cell. Those that's outside, we consider them contributing to other unit cells, so we don't draw them.
Okay.
Yeah.
Then for the atom that is inside the same cell, would it will usually be inside the cell, right? Rather than yeah, it will be inside the cell, right?
Or on the cell lah.
Yeah.
I mean, those at the corners are on the cell. It's
Yeah.
not exactly totally inside. They're just sitting on the corners.
Oh. Okay.
So yeah. So I guess bottom line is that they are either in the cell or on the cell.
Okay.
Right.
So for an atom that's on the cell, would the next bonded atom be inside the cell?
The next bonded atom.
Yeah, the atom that's bonded, would it be inside or also on the cell?
The next, you mean its neighbors, is it?
Yeah.
Its nearest neighbor?
Yeah, the nearest neighbor.
No, the nearest neighbor, it depends. Like, for example, if you look at this guy, right? Okay. So the nearest neighbor will be here to here to here, here to here, right? And then he has one here and one here. So for this particular guy, two of it will be out. Two of it is in.
Okay.
So it depends on which specific atoms you're looking at. Their position will be different. Like this one here, right? Okay, this one at this corner. It's going to have one here, and then one here, and one there. So this 4 is actually outside the cube.
I see.
Yeah. So it depends on which atom you're looking at. Their nearest neighbor may be partially in the cube, or it can be totally out of the cube, or it can be all in the cube.
Alright.
Yeah, the all in the cube one actually is just this guy and this guy, and this guy and this guy. Right, the nearest neighbors are all there. They are not outside the cube.
Oh, okay.
Yeah.
Hello, Prof.
Yep.
You were talking about the two properties of the diamond crystal structure. I couldn't catch the first one.
The two properties of the diamond crystal structure. Okay, which one are you referring to?
I wrote down here like something about bond pairs at the lattice points being parallel to each other.
Bond pair at the lattice points being okay, right. So basically what I'm trying to say is that to construct the diamond structure from the face center cubic lattice, right? What we do is that we put this basis of atoms. That means this atom pair that's inclined at the same direction as the main diagonal of your cube at each of the lattice points. So so if you place this at this lattice point, for example, then you get this arrangement, right? If you place it at this position, then the other atom will be in this position. And notice that this direction of the basis pair is parallel, right? This will be parallel. This is all parallel now. So in fact, for each of the other lattice points, you also should have, this parallel bonding to a neighboring atom there. But each of these, the pair, the other atoms in the pair is sitting outside the cube. So typically we don't draw them because they don't contribute to the cube.
Okay, so all lattice points and all face points have parallel bonding.
Yeah, that's right.
Then points inside don't have may not necessarily have parallel bonding.
Points inside. Points inside, like which point? Do you have a specific?
Like the one that's bonded to the bottom left lattice point.
The coordinate, which one?
0, 0, 0. The one that's bonded with 0, 0, 0.
Oh, this guy?
Inside. Yeah.
Yeah, this is in the volume. But this particular atom is not sitting at a lattice point, right?
Yeah.
It's collectively we consider it as this pair sitting at a lattice point now, which is here.
Oh, okay.
Yeah.
All right, thanks.
Okay.
Professor.
Yep.
Sorry, can I ask another question? Like, is it for all the distance or like the bound length between each atom will all be 1/4 of m, or only for lattice points?
No, not necessarily lattice point. So so in this, okay, give me a minute. Okay, so in this case, what you find is that we say that this is 1/4 of m, right? So we look at this tetrahedral structure where you have the nearest neighbors, the 4 nearest neighbors is 1, 2, 3, 4, right? The bonding distance, okay, to the 4 nearest neighbor, okay, this 4 distance is all 1/4 of m.
Oh, okay.
Yeah, so the distance are all the same.
Okay, then sorry, just to clarify again, the lattice points refer to the 1, 2, 3, 4, 8 corners, is it?
8 corners and 6, which is 1 on center of each face. That's the FCC, right?
So it's just to take out the 4 inside the volume.
Yeah, if you talk about lattice points, the lattice points is okay, let me just. Okay, if you just look at the lattice points, obviously for FCC is here, 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 right? The 8 corners.
Yep.
And then the center of each face. Okay, the center of each face, which is this. Okay, then there's one that corner here. So if you just look purely at the lattice points, then actually you would not have the 4 atoms in the body, right? Yeah. So these 4 atoms in the body actually comes about because in the case of diamond crystal structure, we don't just put 1 atom at each of the lattice point. You actually put a basis of 2 atoms at each of the lattice points, which resulted in this extra 4 in the body.
Oh.
Yeah.
Okay.
Yeah. So why only 4, you may ask? Because the other ones, right? The other ones, they are neighbor, they are pair. The other atoms are all outside the cube.
Yeah.
So if they're outside the cube, we don't consider, right? So if you just consider those as inside or on the cube, then this is what you have left, you know. 8 at the corners, 6 on the center of each face, and 4 in the middle. I mean 4 like within the volume, not exactly in the middle.
Okay, thank you.
Sir, how do you calculate the number of atoms in unit cell again?
Number of atoms in a unit cell. Okay, so to determine number of atoms in a unit cell, right? Then you have to consider for each of the atom, how much of the volume of atom is in the unit cell. Take for example, for this atom here, right? It's fully within the volume. So in this case, this guy will contribute 100% of the atom. So it's one atom, right? If you look at let's say the one that is at the center of the face, this guy, okay? If it's at the center of the face, if you try to imagine, half of it will be within the unit cell, the other half is actually outside, right? So for this red one, you'll be contributing half of its volume, which is 50%. So this guy contribute half an atom. Okay.
So when they ask you in like if they ask you in like if they ask you what's the because I saw the tutorial question like what's the number of atoms in like a unit cell, then you know must you memorize the structure of all these? Then we
no need. The structure just have a general understanding. In fact, if you understand what I was talking about just now, right, the FCC, you put 2 atoms at each corner, you can just quickly reconstruct back and draw the diamond structure already, right?
Oh, okay.
Yeah. But I would say most times we will give the structure if we need calculation. Unless, of course, we want you to describe the diamond crystal structure, then you probably have to sketch it.
Okay.
Yeah.
Sorry, Professor, may I ask a question, please?
Yeah, sure.
So may I clarify that on this diamond structure, is it possible that we translate the lattice coordinates along the direction of the diagonal so that the points that is inside the cells currently can be on the 8 corners, and then the same pattern will be formed?
Translate at the 8 corners.
Yeah. So what if we let the atom that is on the right, top right corner become the atoms on the lattice?
Top right corner. You mean this atom?
Sorry. No, it's as in within a pair of atoms. What if we let the top right one be on the lattices?
Oh, this one?
Yeah.
Be on 0, 0, 0, you mean?
Yeah.
Yeah, if you shift this unit cell to this guy, then you will, you can still get back the. You're asking whether you can form a unit cell from that.
Yeah. Do we still get back the same pattern?
Yeah, you will because it's periodic, right?
Okay, thank you.
Yeah, you will.
Can I see the last slide again?
This one?
Yeah, okay, thank you. I'd like to ask... Oh, wait, never mind. It's fine.
Hi, Professor.
Yep.
For the crystal structure, if it does not label out, like it does not show you what the cube is like. It just show you the entire structure. How do you find the lattice point?
How do you find the lattice points?
Yes, because it will be very disorientated.
Yeah, well, you're talking about a general case, is it?
Yeah.
Because actually, to tell the truth, I mean, for the semiconductor that we are studying in this course, it's well known already, so it's more about understanding and just remembering it. If you talk about any crystal, if you go into a crystal and you try to work out, then you basically have to identify the repeating patterns or atoms to identify the unit cell.
Okay.
Yeah. But in most cases, the semiconductor ones is very well studied. So for the different types, we know exactly what the unit cells already, you know. So it's more about just learning it and understanding the properties and be able to calculate some of the basic crystal parameters.
Okay.
Yeah.
Okay. Thank you.
Okay. Okay. Okay, actually it's more than 10 minutes already. Okay, I suppose everybody should be back, right? Yeah, okay. Okay, let's continue. Now, to understand how the energy band structure of a semiconductor actually comes about, we have to first look at the simplest case, right? If you look at a semiconductor crystal, we know that it's made up of a lot of atoms that is assembled together, right? And then they have this bonding, and you get a solid with a lot of atoms connected together. So in a way, I guess you can think of the semiconductor crystal, right, a piece of crystal, as essentially like a molecule, okay, because it's a lot of atoms formed together, right? I mean, it's not molecule in a conventional sense, because there's so many atoms. It's like a super molecule, you know, that has come together and form a bonding. So then the fundamental question is, how does this bonding and atoms coming together give rise to the energy band structure of the semiconductor? So before we actually go into that, right, to understand this mechanism, it's instructive to first consider the simplest form of molecular bonding. Okay, so here we can look at the simplest form, which is this hydrogen molecule, okay, which is just two simple hydrogen atoms with one proton, one electron, right? What happens when you have these two molecules coming together? So the hydrogen molecule is essentially sort of bond together through the same process as silicon, right? Through covalent bonding, they share electrons. Let's see how, you know, in putting two hydrogen atoms together, their band structure actually change. Okay, so in terms of definition, we can write down the electronic configuration of hydrogen atom as 1s superscript 1. That means there's one electron in a 1s subshell, and the wave function of this electron, okay, in terms of the state that it's occupying, we can denote it as psi with a subscript of 1s, okay, indicating that this is a wave function for the 1s state. Okay, so when you put two hydrogen atoms together, right? In other words, if you look at this illustration here, we have this hydrogen atom A, okay, coming close to another hydrogen atom. Okay, so initially when they're far apart, you have these two electrons having the same state. Okay, so when they're far apart, they don't see each other. It's okay for them to have the same state. Now, when you put them close enough and the electrons, right, the respective electrons start to see one another, then there's a problem. Okay, because in quantum mechanics, what you find is that according to the Pauli exclusion principle, right, okay, each state is actually forbidden to take more than one electron. Okay, so every state can only have one electron. You will not find a state having 2-3 electrons sharing the same state. Okay, so when you have these two hydrogen atoms coming together, and initially if they're of the same state, then it creates a problem, right? In order to accommodate one another as you put them together, what you find is that the energy levels actually will interact, and they actually split. Okay, they actually split into now two levels, EB and EA. Okay, so this EB and EA are essentially kind of like molecular energy now. Okay, and in splitting this, right, what you find is that this EAEB, each would have a total of 2 states in it. Okay, and because when they come together, you have these 2 states that is now created, and they actually share the electrons, they bond, and the 2 electrons now of the molecule will all sit at the lowest energy level EB. And this is actually expected, right? Because in any particle system, the particles will always try and go to the lowest energy level they can find. Okay, so you can understand this from the classical view of, let's say I have some balls, right? If you put some balls and you put it on a slope, what will happen to the ball? You put it at the slope, the ball basically will roll down, right? Because the particles will try and find the lowest energy level that it can occupy, which is down. So they tend to roll down, and they reach the ground level, then they will stay there, right? As long as there's no slope leading to a lower energy, they will just stay there. Okay. So similarly for quantum mechanical particles like electrons, you find that if there's no energy provided, right? So here essentially we're talking about 0 Kelvin or very low temperature. Then the electrons will basically find the lowest energy level you can find, which is EB, and they'll occupy the energy level. And at this energy level, it will basically have two spins, right? Spin up, spin down, total of 2 states. So you can accommodate, the 2 electrons from the molecule. Okay, so this is what will happen when you put 2 atoms together. Okay, because when you put them together, then the electrons originate at the same state, they see each other. That's forbidden. In order to accommodate one another, they have to be different. That results in the splitting of energy, okay, which leads to this condition here, right? You get 2 energy levels now, with 2 states at each energy levels. Okay. So this energy splitting is an important consequence of bringing atoms together. Okay, and it happens to silicon or semiconductor crystals as well. When the atoms comes together. The respective energy level EA is called the anti-bonding energy. EB is the bonding energy, right? So that's just notation, the name that's been given to this new energy levels. And in fact, if you look at how this splitting of energy changes, right, as you change the distance between the atoms, as shown in this graph here, where the vertical axis shows the energy, the horizontal shows the spacing between the atoms. So initially, when they're far apart, then the electrons basically can have the same state, okay? But when you put them together, they start to see each other, and it becomes forbidden, and the energy level actually has to split. And you find that the splitting actually becomes more pronounced as you squeeze the atoms closer and closer together. Okay. Notice that here we have drawn 2 boxes indicating the states that can hold 2 electrons. The upper one is empty, lower one is occupied by 2 electrons. Okay, indicated by the arrow to specify a spin out and spin down electron. Okay. So what we learn from here is that when you have atoms that come together, right, the energy will split. Okay, in order to accommodate the fact that initially they are the same state, which is forbidden. When they come close together, then they will split. And the other thing is that the closer the atoms, right, the interaction become more intense, and the splitting become more pronounced. Okay, so you see that the gap between this splitting actually becomes more as you go closer. Now, one thing to take note is that the number of quantum states before interaction for the whole system is essentially the same as the total number of quantum states after interaction. In other words, if you look at the 2 individual hydrogen atom, right, the initial states at the 1s level of each is 2, so total is 4 states. When they interact and they split into 2, right, remember the upper and the lower state also, you can take a total of 2 each, so the total sum of states doesn't change, it's still 4, okay? The same goes for the electrons, right? Number of electrons before interaction and after interaction stays the same. You don't get, after interaction, you get, say, 3 electrons. It doesn't happen like that, right? You don't get electrons that is created. So number of electrons, number of states stays the same. So if you understand that, and if you now consider the case of a semiconductor crystal like silicon, and in the case of a piece of silicon crystal, it is essentially a lot of silicon atoms that is put together to make that silicon crystal, right? So if you start from a silicon crystal with the silicon atoms in the respective lattice position forming the crystal, okay, so our starting point will be if we were to explode this silicon crystal and move all the silicon atoms far away, right? So anyway, collectively, this total number of silicon atoms, let's say there's n number of it. Okay, this n number of silicon atoms, if you push it together, then they will form essentially the crystal, right? Okay, so we start with this n number of silicon atoms that's far apart. They don't see each other. Then essentially you're going to have collectively, right, of this n number of silicon atoms, you're going to have a total of 2n or 1s state, because each silicon atom will have a 1s state, okay, or 1s level with 2 energy state, spin up, spin down, right? So total number of states that you have will be 2n, because you have a total number of n silicon atoms. N silicon atoms, each having 2 1s states, right? So number of states that's available is 2n collectively, right, of this whole system. Similarly for the 2s, each is 2. If you have n atoms, then it's 2n. Okay, so if you do that, then you can write down the total number of states that is available for this collection of silicon atoms, right? So 2p will be 6n, right? Because 2p can take 6 electrons, and so on and so forth. The total number of electrons at each of this state, you can also write down, okay? Because we know that for a single silicon atom, 1s state, there's 2 electrons. So if you have n silicon atoms, there's 2n electrons with that state when they're far apart. And 2s will be 2n, 2p is 6n, and so on and so forth. Up to 3p, in the case of silicon atoms, the 3p is only 2 electrons there. So the number of electrons, total number of electrons you find there will be just 2n. Okay? So so that's kind of like the number of states and number of electrons that you have for this collection of silicon atoms.
So sorry, what do you mean by number of states? Is it just number of orbitals?
Not just orbitals, because the orbitals itself, yeah, well, I guess you can call it orbitals. Orbitals plus the spin.
Oh,
yeah.
Okay.
So that means how many electron can be in that particular behavior.
Oh,
The spin is also considered a behavior.
okay.
Yeah. Okay, so in the case of silicon crystal, we mentioned that they are held together by covalent bonding, right? They share electrons in the outermost shells, okay? So it's in fact the outermost shell electron that is interacting. Okay, that's something that you need to bear in mind. And so with this n number of silicon atoms that is initially far apart, if you slowly bring them together into the lattice structure, right? If you compress it until they come closer and closer to the equilibrium lattice position, right? Then this is how you expect the energy levels to change. Okay, so this diagram here shows the electron energy in a vertical axis, and R at the bottom is the spacing between consecutive silicon atoms. Okay, so if you look at how it changes, right? So at the lowest level, that's the inner shell, that's the 1s subshell, followed by 2s, right? And then you have the 2p. And the upper 2 is actually the 3s and the 3p. Okay, so here we are looking at collectively the whole system of n silicon atoms. Okay, so when you have the atoms that is far away, that means R equals to infinity, right? So at this position, okay, if you consider it as a system, the energy levels in this system is this discrete level. Okay, this 1s, 2s, 2p, 3s, 3p. Because they are far away, they don't see each other, right? So they stay as this single discrete levels, okay, collectively as a system. And in each of this level, you have the respective number of electrons and states. So for 3s, as we showed in the table earlier, you have 2n states, 2n electrons. In the 3p, 6n states, but only 2n electrons. All right, that's when the silicon atoms are far away. Now, what happens when you start to push them closer and closer together? In other words, you move towards the left side. Okay, so we move towards the left side of the curve. You're basically bringing the silicon atoms closer and closer together. Okay, so as you bring them closer and closer together into the sort of equilibrium spacing, right? You find that up to a certain point around here, you notice that the 3s, 3p levels actually starts to split, right? You get this splitting effect. Okay, and this effect is essentially the same as what happened when you have hydrogen atom coming close together. The outermost electron, okay, in this case, 3s, 3p, they start to see each other. And because they see each other, then in terms of quantum mechanics, it's actually forbidden for them to occupy the same state. So how are you going to accommodate so many numbers of electrons with the same state? So the only way to do that is to basically, having the energy level split. Okay, so the whole system of atoms try to accommodate by splitting the energy levels. So what you see here is, for example, the 3s levels splitting, not into two levels. Actually, this splitting here, it's into a combination of levels. Okay, so what you're seeing here is not just two levels, right? If you're to zoom in, right? If I zoom into here, right? Okay, if you zoom into here, then what you see there is actually not just two level. Okay, within this two levels that is shown, there's actually a lot of fine energy level in between that is closely spaced. Okay, because this is not like hydrogen anymore, right? Where there's only 2 electrons in total and it splits into just 2 level. This is n number of, or 2n numbers of electrons that is there having the same state. So in order to accommodate 2n number of electrons, they have to split into multiple energy levels to accommodate this 2n number of electrons. So what I'm saying is that what you're seeing here, right, it's actually not just 2 levels, it's actually a band now. They are so closely spaced that we can treat them as a continuous level. Okay, so it actually splits into this continuous level. And the same goes for the 3p subshell level. Okay, this is also splitting into a band. All right, this is a band. It's not just 2 level. Okay, to accommodate this very large number of electrons that's present. And as you push the atoms closer and closer together, the splitting become more pronounced. Like what you see in the case of hydrogen atoms, right? Remember we said that when we push it close together, the splitting of the energy level become more pronounced. Okay, becomes more. So the same goes for these silicon crystals. So they'll split and split, okay, up to a point where suddenly you notice that the splitting is so large that they start to touch each other and you get this overlap, okay, and they will basically merge into a single band in this separation here, right, between this separation. Okay, they actually form into a single continuous band. All right, and in terms of where you will find the electrons. Okay, so in this part where they merge together, right, the electrons will just fill up the lowest energy region. Okay, because in this case there is more states than electrons, so there'll be some part of it that is empty. Okay, remember just now we also say that the number of states, number of electrons doesn't change. So when they merged, right, when they merge in this combined region, the number of states that is present there will be 8n. Number of electrons there is just 4n. So it's only half the states that's occupied. Okay, and as you push it even closer, so this is not the equilibrium spacing yet. Equilibrium spacing is actually here, right? This is the equilibrium spacing that will give you the crystal, semiconductor crystal. You find that as they move even closer, this continuous band then split again into 2 separate bands, right? One here and one here. Okay, with a gap in between. So this gap here doesn't have any states. So take note that this band here and this band here is different from the initial band here and the initial band here. Okay, this is actually the mixed up band already. It's not the original 3s and 3p band. Okay, it's like an intermixed, and then they split into these 2 final bands. And what you find is that these 2 final bands, the upper one has a total of 4n states now, unlike the initial, right? The initial is 6n. Okay, after they interact and they split again, it's just 4n, and the other 4n is in the lower part. Okay, and from here onwards, of course, if you reach your equilibrium spacing, right? Once you reach your equilibrium spacing here, then you get this gap which separate the upper and the lower. If you push it even closer, then the gap would increase. Okay, and the energy get pushed upwards. Okay, but if not, equilibrium spacing, right? This is the equilibrium spacing that you will find. Okay, that is stable at room temperature. Okay, so that's what you get. Okay, so at room temperature, this is the band structure of your semiconductor. Right. Now, one thing to take note is that the lower part, right? Notice that the lower portion, right? The lower portion, the 1s subshell, the 2s, 2p subshells, up to this equilibrium position, you still see them as a single level. They don't split. Okay, and the reason is very obvious. It's because the inner ones, right, are further apart from one another. So even if you bring two atoms together, which are the ones that will see each other first? It's the outermost ones, right? Because you look at the crystal structure, you know, it's the outermost ones that is sharing the electrons to form the bonding. Okay, so those that is inner to the atoms, they don't see each other yet. Okay, that's why up to the equilibrium spacing, they stay as a single level. Okay, but if you notice, if you actually were to squeeze the atoms even closer, right, beyond the equilibrium position, okay, you notice that at this position, the 2s, 2p subshells levels actually start to split also. Okay, so you need to push that even closer up to a stage where they sense one another, then you get the splitting as well. Okay, so if not, for semiconductor, right, that we used, obviously we operate them at this equilibrium spacing. Okay, and this is essentially the structure that we're looking at. Okay, this is the structure that we work with. Okay, so the part that's important is actually this equilibrium spacing. I mean, the subsequent ones, we are just explaining it to give you an idea of how it comes about. Okay, so really the one that we looked at it's just this slice here, right? Okay, it's just this slice at the equilibrium spacing. Okay, that's of concern to us. Because if you work with a silicon crystal at room temperature, that's the separation of the atoms that you'll find, and this is the band structure of the semiconductor. So in other words, when we analyze a semiconductor and look at the band structure, we just take this particular slice here at the equilibrium spacing. Okay. So in other words, if you take that out, this is effectively what we would typically draw. So if you have a piece of semiconductor, right? So here, if you have a piece of semiconductor like this, okay, and at each point in the semiconductor, the energy structure is basically just upper band and a lower band, right? Okay, and if you go to another position in the crystal, it's the same, right? You have an upper band and a lower band. So in other words, if you were to draw the energy band of the semiconductor along the x-axis direction, which is in fact what we are showing here, right? If in the x direction, you know, this band diagram, the energy levels that the electron will see as it moves from left to right will be these two horizontal lines. Okay, so the upper region and the lower region, right, is called the conduction band and the valence band, respectively. Okay, so going back to this figure, okay, this upper part here, this is called the conduction band. This part at the middle, at the lower part, is called the valence band. Okay, and then obviously there's a band gap in between, a gap where there's no states. Okay, so upper part is called conduction band, bottom part is called valence band, and the edge of the conduction band is typically denoted as EC. The top of the valence band is denoted as EV. Okay, so so if you have, for example, electron that is in the semiconductor that's free to move, right? Then in the band diagram, because it's free to move, that means it's not bonded, right? Then in the band diagram, we'll draw it as being in the conduction band because it's free to move. You know, so when it moves, this is the direction that you move in the x direction. Okay, so take note that in this band diagram that we are showing, right, the horizontal axis is the physical position in the crystal. The vertical direction is not the physical distance in the crystal. Okay, take note that this vertical direction is the axis of energy. Okay, it basically shows you what is the energy of the electron at this position. Okay, if in moving from this position to the next position, right? Let's say here, let's say the electron actually gain energy, then in the Venn diagram, we'll draw it as going up to higher position, right? Because if it gain energy, then it must go up in the energy axis. So horizontally in the piece of semiconductor, let's say it move horizontally, in the Venn diagram, you'll move up because the energy increase, right? So increased energy means you go higher. So in this case, you move up. All right. So here you have to be very clear. The vertical axis is energy. It's not position. It's energy. Okay, take note of this. Now, what happens when you apply an electric field to the semiconductor crystal? Okay, so again, the same piece of semiconductor, for example, right? And when there's electric field that's applied to this, okay, for example, if we were to connect this to some voltage, right? Okay, let's say I connect this piece of semiconductor to a power supply, where the left side apply to positive voltage, the right side apply to negative voltage. Okay, so right side is negative voltage, left side is positive voltage. Then the Venn diagram will basically take on a gradient. Okay, the Venn diagram now will take on a gradient and it will tilt in such a way that the side that is negative will be up and the side that is positive, it will tilt down. So you get a gradient with negative that is higher and positive that is lower. Okay, so if you have a electron that is in the semiconductor, right? Let's say electron here. If it is negative on the right, positive on the left, which direction will the electron move? Electron will move to the left, right? Okay. If electron move to the left in this Venn diagram, you expect this to move left also, because if you look at it, right, the electron now is sitting on a plane that is inclined, and you tend to roll down, okay, to the lower energy side. Okay, so that's how the Venn diagram would change. You put a voltage or potential, the negative side will push up the energy Venn diagram, positive will push it down. Okay, and this is consistent with what you will expect. Okay, because if you put positive on the left and negative on the right, the current, right, the current will flow from positive to negative. Okay, but electron flows in opposite direction to conventional current. Okay, so electron will go left. Okay, which is consistent with what you expect if you analyze the energy Venn diagram. Okay, which is this. Okay, and in this case, because the positive is on the left, negative is on the right, notice that your electric field is pointing from left to right. Okay, electric field is left to right. Electric field always points from positive to negative. Okay, and here you can also show that the electric field, okay, the electric field in the semiconductor is related to the derivative of the Venn diagram, d dx. Okay, multiplied by a constant 1 over q. Okay, the q here refers to an electronic charge, which is 1.6 by 10 to the power of minus 19. Charge unit is coulomb, so it's C. Okay, this Q here is a physical constant, 1.6 by 10 power minus 19 over coulomb. So the electric field is related to the gradient of the Venn diagram. In fact, one of the tutorial questions require you to prove this. Okay, so I'm going to leave it as an exercise for you to think about it. How do you prove this equation based on what you know already about electricity, right? Electric field, voltage. Okay, how do you relate it and try and derive this equation? Okay, go think about it and try this to solve one of the tutorial questions. Okay, one of the tutorial question actually requires you to prove this. Okay, go and have a go, and then tutorial we'll discuss.
Wait, Professor, what's the significance of this equation again?
This equation describes the relation between the energy Venn diagram and the electric field, right? So if you look at the description, right, it basically says that electric field is given by the derivative of the energy band diagram, which means that if you interpret it, it basically means that if your energy band diagram has a gradient, that means it's tilted, there must be a presence of electric field in that region where it's tilted, right? Does it make sense?
Yes.
Yeah,
Thank
yeah.
you.
So okay, so then the question is, how do you prove this? Okay, this is a tutorial questions. Go have a go and then see what I can prove.
Sorry,
Yeah.
Professor.
Hmm.
What does E and the fancy E symbol represent?
Oh, okay. This is a Greek Greek symbol E, right? It's electric field.
Then the English letter E.
Energy, electron energy.
So is it the electric potential energy?
Yeah, it's either the EC or the EV.
Okay. Then X is the physical.
X is the physical distance.
Distance.
Yes. Which is.
Okay. Thanks.
Yeah.
Okay.
Hello,
Yeah.
Professor.
Yeah.
If you apply the electric field on both sides of the semiconductor, does it mean that the field is possible that two quantum states may have the same energy?
Two quantum states have the same energy.
Yes.
Two quantum states. No, it doesn't. This just basically shift the energy levels, but the energy state structure is still the same. It just shifts the relative positions of the structure.
Yes, but some of the, I mean, like some quantum state on the left, the energy will be lower. Then, does it mean that, like, for example, previously
the energy will be lower, but the state is the same. The state doesn't change.
Yes, then two different quantum states may have the same energy level.
Two different quantum states may have the same energy level.
Because the left side is dropped down.
Not exactly lah, because when you have this situation, it kind of manifests in the form of kinetic energy if it's moving. So in terms of the intrinsic energy state, it's still the same. The difference is essentially described by the possession of kinetic energy.
Oh, okay.
Yeah, so it doesn't conflict.
Okay.
Yeah.
Thank you.
Okay, so oops. Okay, so I'll just continue. Okay, so we mentioned about electrons and holes in a semiconductor. Okay, the semiconductor actually have two carrier types. It's not just electrons. There's actually another type called the holes. And so the electrons in the valence band, which is the lower band, can actually be promoted to the conduction band by these two mechanisms. Okay, either you increase the temperature of the semiconductor, or you shine light with a suitable wavelength on the semiconductor, and you will give it enough energy to go up to the conduction band. Okay, so
Sir, can I ask a question?
Yep, sure.
If the valence band also has a gradient when there's electric field applied, then why do the electrons have to be in the conduction band for there to be a current?
Okay, maybe let's maybe here is a good place to start. Okay, so the valence band is actually all filled with electrons, right? And so first of all, these electrons in the valence band basically corresponds to those electrons in the covalent bonding. So it refers to all these guys there, right? So as you can see in the covalent bonding, they are participating in the bonding and they are essentially fixed in position. Okay, they cannot move. Okay, in order for them to move, there must be some empty states for them to move to, right? Because if you think about it classically, you have a ball that is moving, the energy is increasing. So if the energy is increasing, there must be some states at higher energy that it can go to. Okay, so if those are not there, then those particles cannot move. Okay, so those in the valence band actually cannot move because it's all filled up with electrons. So in order to move, if you were to say, for example, be able to promote an electron from the valence to the conduction band, then once the electron is there, you'll basically see a lot of energy states that you can go to in the higher energy level. So if I give it a little bit of energy, right, by putting electric field or something, right, then you will find that you can gain energy and there's a state that you can go to increase in energy. Okay, then it becomes possible for the electron to move. So in order for electrons to move, basically what I'm saying is that it has to go to the conduction band so that there's empty states for it to go to, for it to move. Okay, so that's kind of like the idea behind it. So how do you get electrons to the conduction band? As I mentioned, one of it is by providing energy through increasing the temperature. Okay, so if we can increase the temperature of the semiconductor, that could provide some energy that can bring the electrons up from the valence band to the conduction band. And physically, right, physically, that corresponds to electron breaking the covalent bonding and becoming free to move. Okay, so this electron that you see here corresponds to this electron in the conduction band. So once it's free from the bonding, then it will be in the conduction band. Notice that when this electron takes off from the covalent bonding, it actually leaves behind a vacancy, right? When it's all there, the net charge in that region will be 0, okay, because the number of protons and electrons are the same. Now, if you pluck out an electron, then what you find is that the surrounding region, there'll be one more proton than electron. So what you find is that this missing covalent bonding, right, this incomplete covalent bonding would carry a net charge of positive Q. Okay, so the charge will be the same as the electron, except that it's positive. Okay, so this vacancy here is what we call a hole. Okay, so this hole, right? This hole, it turns out that it can actually move. Okay, look at this illustration, right? Let's say at time t1, you have a hole that is created at A. Now, suppose another electron from a neighboring silicon-silicon bond can actually break off. Right? Let's say the temperature is sufficiently high. This guy here can break off and it can find its way to the hole at A. So it can take off and take over the position at A. So when it does that, what you find is that the initial hole at A is now complete, so the hole disappears. And from this position where the hole takes off, right, where the electron takes off, you now have that vacancy created. Okay, so if you compare time t1 to a later time t2, the hole initially is a position A. After some time, it could move to position B. Okay, so it kind of appears that the hole is moving. Of course, in reality, it's actually the electron that's moving, right, to cause the hole to appear to shift in position. But anyway, this apparent moving of the charge is easier analyzed if you treat it as a particle. Okay, so instead of thinking of this as a vacancy, we think of it as like a particle. It's actually a virtual particle, right? Because it carries a charge and it seems to be moving. So over different time, depending on which electron comes off and take its position, then the vacancy will shift to another location. Okay, so if you look at it at a macroscopic view, it will appear as if the hole has moved from A to B and then to C, right? So it's appearing as if it's a particle that's moving. Okay, so to simplify the analysis, generally we just treat it as a particle, okay, a virtual particle, so that when you analyze it, it's a lot easier. Okay, so that's what the hole is about. So when the hole is moving like that, it corresponds to the hole moving in the valence band. Okay, right? It corresponds to the hole moving in the valence band.
Sir, can I ask, what initiates the movement of the electrons? Is it a difference in energy levels?
Okay, if there's no electric field that's applied, where there's thermal energy, this electron will basically move based on thermal motion, right? They will basically knock around because they have thermal energy. So this movement is not directed, it's just randomly knocking around.
Oh, so how does supplying the temperature, what does it do? It makes that does it allow them to overcome the bond, or does it like provide a energy gradient between?
No, it doesn't provide energy gradient. I mean, here when we talk about temperature increasing, we are saying that throughout the semiconductor, the temperature increases uniformly. So there isn't a temperature gradient. So everywhere is the same temperature.
Okay.
So the only difference is that with the presence of thermal energy, it could allow some electrons to gain sufficient energy to break off the bonding. And this breaking off of bonding corresponds to electron going from valence to conduction band. In turn, it actually leaves behind a vacancy, which we call a hole. So in other words, in a pure semiconductor like this, it always creates the electron and holes in pairs. So we call this electron hole pair. Right? Wherever an electron is created, you would expect a hole to be created as well in a pure semiconductor. Right? Because in having one electron in the conduction band, you must have a hole in the valence band. Because the mechanism in which they are created is from breaking the bond. Right? So you're going to have one free electron and one vacancy in the bonding, which is a hole. Okay.
I'd like to ask something else.
Yeah, sure.
So the electron that gets broken off, is it able to now freely move about in the silicon crystal?
Yes, correct.
I see.
Yeah. And so is the hole. Okay, the hole, because it's in the bonding, right? It can also move quite freely.
But the hole will only move to the bonded electrons, right? That's something like that.
Correct.
Yeah,
Yeah.
okay.
So it moved from having electron breaking bond from a neighboring location, taking its place, and the vacancy basically shift to another location. I mean, the actual physical moving is by the valence electron, but when we analyze it, we just treat it as actually the hole moving. It's equivalent, in terms of analysis, it's equivalent. So that makes it easier, right? So in other words, we just think of positive charge moving instead of negative charge moving in the opposite direction, which is more tricky to analyze.
So also, when will it lead to breakage? Like if you remember the first graph that you showed us.
Yep.
When V goes in the opposite direction and then goes immediately down to the bottom. When will that happen?
That one will happen when you apply a voltage across the semiconductor. That means you connect it to a battery. Yeah. But here, what we're talking about is just a semiconductor sitting on the table. You don't apply any force, any voltage, any magnetic field. Just sitting on the table, just based on heat. This is what will happen. You have electrons and holes that's created, and they just randomly move around in the crystal.
Okay.
Yeah. Okay. All right. So yeah.
For the movement of the hole, does it have to move from bond to bond, or you can skip bond? Skip bond.
Strictly speaking, the hole will move from bond to bond.
Okay.
Yeah, but because because in the first place they are such small structure, so the movement will not be discrete. It won't be like a very obvious discrete movement from bond to bond because in the first place they are so small. So in a macro view, you appear as if they are moving continuously.
Oh, I see.
Yeah.
I thank you.
Okay. So the other mechanism that you can create electron hole pair, as I say, is by shining light. Okay, so as we talked about in the first lecture, we can think of light as being made up of packets of energy. Okay, and it turns out that this packet of energy, okay, the amount of energy that each packet have is defined by this equation here, right? Energy of each of this packet, each of these photons, is defined by h nu or hf. Okay, this h nu here, this nu is referring to the frequency of the light. Okay, you can also write it as hf if you define frequency as f. But if not, we use this Roman letter nu, right, which is a curly v to represent frequency. Okay, turns out that the energy of each packet of this light is just h, which is the Planck constant, multiplied by the frequency of the light. And if you convert it to wavelength, it's just hc over lambda, right? Using the equation of a wave equation, c is equal to f lambda, right? You can show that it's can be converted to hc over lambda. Okay, so what that means is that the energy of each photon increases with the frequency of light, or it decreases with the increasing wavelength. Okay, so if wavelength increase, the energy of the photon decreases. So in order to excite an electron from the valence band to the conduction band, the minimum energy of the photon that's required is actually equal to the gap, the band gap, right? You must give it enough energy so that you can at least cross the band gap. Then there's a chance for it to get into the conduction band. Okay, so the necessary condition for light to create electron hole pair is actually this, right? The energy of a photon must be at least equal, if not greater than the band gap. Okay, so if we write down this equation, then you can find out the limit on the wavelength in this case. Okay, so there's some wavelength where you have to have in order to have electron being promoted to the conduction band. So in this expression here, right, in this expression here, you notice that we are convert this into 1240 from the physical parameter. Take note that in this expression, okay, take note in this expression, the units of EG is actually EV, okay? And the units of lambda is in nanometers. So if you do try and convert by putting in all the parameters, H will be 6.6 by 10 power minus 34, all right? And C is the speed of light, 3 by 10 power 8 meter per second. If you put in those figures, right, if you do in those figures, you will not get 1240. Okay, you need to normalize out the lambda and the EV as and the energy as EV and nanometers. Then you will get 1240. Okay, so after this lecture, go and verify this. Just convince yourself that if you convert it according to this unit, you get 1240. Okay, so in other words, if you want to use this equation, right, you know, use this equation, and suppose the wavelength is let's say 800 nanometers, right? If you put this into the equation, then the lambda value here that you use is actually 800. Okay, because the nanometer has been normalized out already, so just put in the value corresponding to that unit. And when you divide it out, okay, this value here will have a unit of EV. Okay, you have a unit of EV.
Sir.
Yep.
What is H represent? Is it
H is a
constant?
Sorry?
Is it just a constant?
Yes, H is a Planck constant. As I mentioned previously, in on Tuesday, right? The H is actually Planck constant. Okay, it's Planck constant. The value is 6.626 by 10 to the power of minus 34. Unit is joules second. Okay, it's a physical constant. All right. So anyway, you can go and figure this out, right? Replace in the constant values and just make sure you know how it gets to 1240. So this is actually quite easy to use in the sense that you know, the energy of photon, you can also write it as you got to convert it and normalize it to nanometers and EV, right? Energy of photon can be 1240 divided by lambda, where lambda is in nanometers. So to find the energy of a photon that has a wavelength of, let's say, 100 nanometers, for example, right? Then all we need to do is, in this equation, we just put in lambda as 100. Then the energy of photon is 1.24 EV. Sorry, 12.4 EV. Okay, it'll be 12.4 EV. Ken? Okay. Okay, so yeah, just to summarize, when you want to create electron hole pairs, you can increase the temperature of semiconductor, or you can shine light on the semiconductor. Okay, light of suitable wavelength. where the energy of photon is sufficient to overcome the band gap of the semiconductor. So of course the thing then is that when you subject a semiconductor to some temperature, right, we say that this will give it some thermal energy, right? Electron can break off from the bond. Then the question you may ask is, in this case, does the electron pair keep creating, right? The electrons break off, does all the electrons start to break off until the bonding is all gone? Then the crystal will basically collapse, right? Because if you take out all the electrons in the bonding, the crystal will basically fall apart, okay? Of course, obviously, it doesn't happen like that. If you put a semiconductor crystal on your table, over time, right, at room temperature, does the crystal disintegrate? It doesn't, okay? For a reason, okay? And the reason is because other than this electron breaking off on the bonding, there's also a countering process called recombination, where this moving electron, as it's knocking around, right, it can see a hole and it can recombine with the hole. That means it goes back to the vacancy and complete the bond again. So this is actually the other countering process. So in a semiconductor, at thermal equilibrium, where electrons is being created, electrons are also being cancelled out. Okay, so this is actually a dynamic process. At equilibrium, this generation and the recombination number is the same. So the net number of electrons at holes that is free is the same. It doesn't change at equilibrium. Okay, so there's actually this countering process of the recombination, right? That is also there. So we call this recombination, where the electrons actually go back and annihilate the holes. That means they cancel out the holes, so they disappear, right? Because once it goes back to the vacancy, electron pair will disappear, right? It goes back to the bonding again. So as I say, thermal equilibrium, or more generally, when we talk about steady state, okay, if you see the steady state term, right, it basically means that the generation and the recombination is the same. So that is steady state. The numbers of the electrons at holes doesn't change, okay? So anyway, this is always there. It's a dynamic process. It doesn't mean that electron break off, then it just stay break off for a long time, right? It doesn't go back. It does go back. So the number of electron at holes that's available is from this dynamic process where some is created, some is cancelled out. So this cancelling out and generation, right, would be equal under steady state condition, so that you get constant number of electrons at holes in the semiconductor at a given condition. Okay. All right. So when we talk about thermal equilibrium, okay, thermal equilibrium is a special case of steady state condition where when you see thermal equilibrium, it means that there is no external force applied to the semiconductor. In other words, it's just a semiconductor sitting there. You don't apply electric field, you don't apply magnetic field, right? Nothing is connected to it. There's no external force applied to it. And that's in thermal equilibrium condition. Okay, so the thermal equilibrium condition, you will have a generation rate equals to recombination rate, and you also get a constant number of free electrons and free holes. Okay, so the electrons that you find in the conduction band are considered free because they can move freely, right? Once you apply a voltage, they can move. So are the holes in the valence band. You apply a voltage, the holes also move in the valence band. Okay, so we find electrons in the conduction band, they are free to move. You find holes in the valence, you find electrons in the conduction band, they are free to move. You find holes in the valence band, they are free to move. They'll conduct current. Okay. Right. So yeah. So this is kind of like the thermal equilibrium condition. Thermal generation rate equals to recombination rate under thermal equilibrium condition. Ken? Any questions? So you need to visualize this as actually not just a static process, right, where electron is created, holes is created. It's always the same electrons at holes in the semiconductor. It's not true. It's actually a dynamic process. So the different electrons that is present, right, although the number is the same at thermal equilibrium, they're actually made up of, on average, different electrons. Okay, some get created, then this same one could recombine and disappear. Another one appears from the generation. So it's actually a generation recombination dynamic process. But on the whole, if you look at it, the numbers are constant. Okay.
So how can we still see a continuous continuous shifting of a valence, but a hole in a if this happens?
Continuous. Sorry, say that again.
When the valence electrons fill in the holes in a valence band, we'll see a similarly continuous shifting of a hole.
Yeah.
And
but at the same time, you also have electron that's created. You know, so you get electrons become recombined, and then electrons will be generated. So it's so the amount that's generated, amount that's recombined, it's the same at thermal equilibrium. So the total number of electrons at holes remains the same under thermal equilibrium.
But this does not necessarily happens on a fixed position, right?
It's throughout. So it's everywhere dynamic. But on the whole, if you look at it, the numbers will be constant everywhere. So on average, you look at it on a macroscopic view, it will be the same everywhere. Of course, if you zoom in, into a very, very small position, some get created, some get recombined. At the localized position, you may see that it will fluctuate in terms of the number of electrons at holes. But if you look at a macroscopic view, it's uniform. It's the same everywhere. Yeah. So in any case, when we analyze a semiconductor, right, we don't analyze a semiconductor that is on a atomic scale, like only 2 atoms apart. Usually, when we analyze a semiconductor crystal, it's easily a couple of micrometer, which is a couple of micrometer would mean that it is if it's say 5 angstrom, you're looking at tens, hundreds of thousands of atoms in that space already. So on a macroscopic view, it's uniform.
Professor?
Yeah.
Is the recombination caused by the difference in overall charge in conduction band and valence band?
Sorry, caused by?
Caused by the different overall charge of the conduction between the conduction band and the valence band. What causes the recombination?
The recombination is a natural process because if you have electrons in the higher energy, remember we say that in this universe the particles generally will want to occupy the lowest energy level possible, right? So although it's promoted up due to the presence of heat, you always try and minimize its energy. So when it goes up and it's all roaming around, if we see a vacancy that's of lower energy, you want to go there, right? So it's a natural process. It's like if I have a table that's full of holes and I roll a lot of marbles on the table, right? And if the marble come to a hole, naturally they want to drop into a hole, right? So it's a natural process.
Okay.
They always want to go to a lower energy possible.
And then one more thing. When the movement of the electron from the lower energy band to the higher energy band is actually it's not really a physical like a vertical movement, right? It's
No.
one
Yeah,
axis,
correct.
right?
Yeah.
It's an
It's
energy
not
axis, right?
correct. It's just the energy increases. So that's why I emphasized earlier, right? If you look at energy band diagram, the vertical axis is actually energy. It's not physical position. So when an electron go from valence to conduction band, doesn't mean that electron jump up. It just means that energy increases sufficiently to cross the barrier of the band gap.
Professor, so my question is, when the electron moves out to create a hole, where does the electron go to then?
Go to where?
Yeah, where does the electron go to?
It doesn't go anywhere. It just okay. So in terms of physically, when it breaks off from a bond, it just comes out of the bond, and with the energy, it can then randomly move about.
Oh, okay.
Right? It just escape from the bond and it can move about.
So it's just basically like a process of exchanging the location of the electrons. They're just changing location.
Yeah. So basically, in other words, it's just going out, right? Correspond to the case where the electron in the bonding have enough energy to take off, and with the thermal energy that it has now, it can sort of random around that region. It can move randomly around that region. Of course, you apply a electric field, for example, a force, then this particular electron that has come off can then move in the direction because of the electric field.
Okay, thank you.
Yeah.
Hi, Professor.
Yeah.
During a recombination, is the energy released as photon?
Okay, this is actually some part that I'll talk about later. So energy has to be released, right? Because there's a change. So this energy can be released in different form. Photon is definitely one of the possible form. The other form that you could give off is heat.
Then how do you know whether it is released as photon or released
This
as
one I'll talk about in later chapters.
Okay, thank you.
Prof, I have a question.
Sure.
So for the thermal equilibrium, is there usually a fixed temperature for the thermal equilibrium?
No. So the thermal equilibrium is talking about essentially the semiconductor stabilizing at under thermal condition. So the temperature wise, it's up to you, right? I mean, depending on what temperature you apply to a semiconductor. So I could bring, for example, the semiconductor to 400 Kelvin, right? If you supply this temperature 400 Kelvin, then at thermal equilibrium, of course, the electron holes in the semiconductor will have to readjust. Because once you increase the temperature, what's going to happen to the thermal generation rate? It will increase, right? Because now heat is more, so you're going to get more electrons that's created. At the same time, if more electrons are created, then electron number is more, and the chance of this electron recombining with holes will also be higher. So you find that recombination also increase. So this increase in thermal generation will also result in increase in recombination until a stage where they balance. Then it will stabilize where the thermal generation equal to recombination again, and that gives you a stable number of electrons and holes. Then that's the thermal equilibrium condition. So thermal equilibrium condition can happen at any temperature.
I see. Okay. Thank you.
Yeah. Right.
So regarding the energy splitting, right? So when the two electrons come together, they will both first go to the lower state, but then one will get pushed to the higher state. Is it?
Yeah. So they basically try to occupy the lowest state possible. So you find that the lowest one get filled up, right, up to whatever number of electrons you have. That's at 0 Kelvin, by the way. If it's not 0 Kelvin, then those at the surface will start to have more energy, then they could actually move up as well. So when you describe the case where they occupy the lowest energy level possible, it's essentially talking about 0 Kelvin. So once you have thermal energy, that's a different case altogether, right? Because those at the higher energy, they will have some thermal energy that can cause them to move upwards.
Okay, and then for inside 3, they say that when both of them decrease the energy state, then that is the bonding energy of the H2 molecule, right? So when one of them then moves upwards, where does that energy come from? Does it take back the energy? Because bond energy is released when the bond is formed, right?
Yeah. So depending on the type of element that's bonding, so it will give off or take out some energy.
Okay.
So in the case of semiconductor, typically we create a crystal by melting, the silicon material, right, into liquid, and then we use a silicon seed to pull out the material, and it crystallize according to that seed material. Then you get this silicon ingot, right? This piece of material that slowly pull out from the melt that will crystallize according to that seed. Then when it cools, then you get the crystal, and then we basically slice it into flat pieces as silicon wafers to make electronics.
But for example, for here when it's H2, right? When they both go into the lower state, that's the bond energy, as in the bond energy, the energy released when they form the bond. So if it has to take back the energy for one of the electrons to go into the higher state, doesn't that mean that there'll be net zero energy released? But then there has to be energy released when bonds form.
There is. Yeah, I think there's some energy consideration there, that you have to take into account.
Okay, So it just takes back some of the energy that is released to go into the higher state.
You're talking about when they go to higher state?
Yeah.
When you break them?
No, when they form the bond and then one of the electrons has to go into a higher state.
When they form the bond, both of them go to a lower state.
Yeah, but then later on, because of the Pauli exclusion principle, doesn't one of them have to go into a higher state?
No. You see, the part where the hydrogen is bonding, right, it splits into two. The thing is that two levels actually have two states there. Remember, each can have a spin up, spin down, right? There's another quantum number which is spin up, spin down. So the combined molecule, hydrogen molecule, actually have two electrons at the bonding energy. The lower one, there's two with different spin.
Oh.
Yeah.
So what in slides 2 and 3, what is the psi A? Like
psi A. Psi A is the anti-bonding energy lah. Because in the splitting process, the my battery is running low, so I may have to end soon. Okay, so in the bonding process, you have this splitting, which creates these two energy levels, and if you think of it as like conserving the number of states, you have two at the bonding level energy, right? Two states, and you need another two at the anti-bonding energy levels. Because the total number of states that we have from each of the hydrogen atom at the 1s level is 2 and 2, so total is 4. So the interaction will produce these two levels with two states each, conserving the total number of states.
So it's like the state is formed, but it's not occupied by any electrons.
Yeah, correct.
I see.
The same as like this hydrogen atom at this 1s state, it actually has two states, but hydrogen atom is such that you only have one electron. So one of the states is actually not occupied,
Okay.
So you can think of it as when they bond, the lower two states is taken up, and the upper two is kind of essentially from this two, right? Okay.
Does that mean that the upper state will be like similar to a conduction band?
No. In this case, it's not. It's not. It's just this is just a molecule, so it's not exactly a conduction band. It's a little bit different. This molecule. It's not a whole solid. And in any case, it's only a single level. It's not a band, so you don't consider this as a band where electron can move kind of thing, because for this electron, in order to gain higher energy, it goes to another state. It doesn't continuously sort of move in a band. So it's a different thing altogether. It's only when you have solid, a lot of atoms come together, then you get this band effect. Okay.
Can I ask a question?
Sure.
For the positive holes that's created inside the valence band, would they also move around within the valence band? As in, like, would they?
Correct. Yeah. So in the case of holes, when we talk about holes, right? If the holes it's moving like this, okay, like what we described, if the hole is actually moving in the crystal, then in the band diagram we will basically see them moving. Okay, we'll see them moving in the valence band. So holes will only move in the valence band. Electron will only move in the conduction band.
Okay, thanks.
Yeah. Okay, I think I have to stop already. My battery is going off soon. Okay, anyway, go and think about this. And if you still have questions during the tutorials, feel free to come and consult again. We can discuss more. Okay, so as I was told that grouping will be made known to you by tomorrow, if I'm not wrong. Okay, so once you know your grouping, then you just come for your tutorial during your allocated slots. Okay, so next week we are starting the tutorial, and the first tutorial question set has been uploaded already for those who don't know. So do try the questions before you come for tutorial. Okay, so I'll see you next week then, right?
So do we need to print out?
Print out what?
The tutorial.
Yeah, I mean, it's up to you. I mean, if you need the questions physically, you have to print out the question paper lah. But if you don't need it, you can look at it on the computer. That's fine as well. It's up to you.
Thank you.
Okay, so right. Okay, that's it then. Take care. I'll see you guys next week then.
All right, thank you.
Okay.
Excuse me.
Thank you, sir.
Yeah. Sure.
May I ask?
Thank you.
Yeah. Okay.
About
Those who are done.
tilting of the energy bar. It's like
Uh-huh.
so. What will happen when a conductor is applied to a electric field? Like, is it also tilted, or is there any difference?
Sorry, for what? For conductor. Are you talking about conductor?
Sorry. Yes.
In a conductor, yeah, you would also tilt.
So is there any difference?
Conceptually, it's the same lah, I guess, except that in the case of conductor, because the number of electrons there is a lot more, so the tilting is not so much, I guess.
Oh, okay. Thank you.
Yeah.
Thank you.
Okay.
So,
Yep.
are you the one recording this lecture?
No, I didn't record.
Oh, okay. Never
Why?
mind.
Why?
I was gonna ask whether lecture recording will be available anywhere.
Oh, yeah, actually typically we don't record. Okay. Yeah, let me explore that to see whether we can.
All right, thank you.
Yeah, we can do that.
Hello, sir. Can I ask you a question? So regarding the electron band, so the graph that shows the different electron bands, right? So I remember there was this part where you said that the electrons go down to the lower band, like from the p orbital to the s orbital.
Yeah.
Why is it that the number of states changes for the two bands? So like for the upper band, it changes from 6 states to 4 states. Okay, 6 n states to 4 n states. Then the bottom one changes from 2 n states to 4 n states.
Sorry. Can you repeat again? I can't catch you there.
So for the graph with the electrons and the different band energy levels, why is it that the lower band for the three s orbitals, why is it that like the number of states changes from 2n to 4n after the connection to the higher like?
Okay. This is because of the interaction between the 3s and 3p subshells. Specifically, why they are like that, you have to solve the Schrodinger equation. It's not something that we can kind of explain qualitatively, I guess.
So we just take it as it is,
Yeah. I think just